So, I will continue with the translating the concepts of simplex algorithm to the transportation array. And so, let me just begin with the first thing that we are going to talk about is the so basic set of cells I am defining now. See, we have m plus n minus 1 linearly independent columns of A, which form a basis for the column space of A, and so then the corresponding cells, as I told you that the 1 here means it is the A11 column, A12, A13, and this is how we had said that the transportation array is represented. So, you take the m plus n minus 1 linearly independent columns of A, and the corresponding basic cells that you the corresponding cells that you will take in the array, they will form a basic set of cells, we will call them, right. And of course, later on I will show you that it is not necessary that every set of basic cells will give you a feasible solution, just as in linear programming problem we saw that every basis will not necessarily give you a basic feasible solution, it will give you a basic solution. So, we will look at that later on. Now, what we are saying is that since the columns I showed you form you can by transforming the in fact just interchanging the rows and the spaces of columns or rows, one kind of transformation you can do, and then you can show that the set of columns, the set of columns of a basis can be reduced to a triangular matrix, right. And so, when you translate that property to these basic cells, basic set of cells, then what will happen is that the following properties you can be seen, that there is a row or a column of the array which contains exactly one basic cell. Now, this is equivalent to the fact saying that in a triangular matrix, you remember if you have a this is all zeros and you have entries here, then the triangular array you see, for example, if you look at this column, then there is only one entry, right, and then when you delete this column and this row, then again there will be only one entry. So, this is the kind of property that you have in a triangular matrix. We are translating it to the set of basic cells, and so we are saying that if there will be at least one row or column of the array which contains exactly one basic cell, and then if you take any non-empty subset of B, then it will also have. So, here I am calling this, I should have said script B. I am denoting by script B the set of basic cells corresponding to the basis B of linearly independent columns which form a basis, right. So, script B, you take any non-empty subset, that will also have property 1. So, this is the translation of the triangular property of the basis matrix to the set of basic cells. Okay. Then another thing, another property that we want to say here is that the basic set of cells will span the transportation array. Now, what does that mean? And I will again maybe just give you a very ad hoc treatment of the whole thing, and then later on when we do develop some more graph theory and for networks, then the things will fall into place. But here what I am saying is that there must be. So, what do we mean by basic set of cells spanning the transportation array? So, there must be at least one basic cell in each row and in each column of the array. So, there cannot be any row or any column of the transportation array which does not have a basic cell present in it. And how can I support, I can support it is by the fact saying that, because you see if the corresponding set of columns B, there is no, because if right, take the basic set of columns, and what we are saying is that if no cell is present in the ith row of the array, suppose B is a set of basic cells and no cell is present in the ith row of the array. What does that mean? That means in the corresponding set of columns B, which is the basis for the matrix A, there is no column of the type EI EQ, because if there is no cell present, say for example, in the first row here, that means I do not have columns of the kind E1 E1, E1 E2, E1 E3, E1 E4, E1 E5. So, similarly here for the when their number of columns is n, I do not have columns of the kind EI EQ for q varying from 1 to n. What does that mean? That means if I take a non-basic column EI EJ, then I cannot express it in terms of the basis columns of B, because since B does not have a column of this kind, you see how will I express this because I need a 1 in the ith place to express this column in terms of the basis columns, but if the basis columns do not have any column which has 1 in the ith place, I cannot express this as a linear combination of the columns of B. So, this will contradict the fact that B is a basis, right, and therefore, this is not possible. So, for each, that means a basic set of cells, there must be at least one cell in each row and in each column, right. And so, now let me try to demonstrate to you what we mean by that. So, for example, if I take this 4 by 5 transportation array and I have this collection of basic cells, then I am trying to show, first of all I am trying to show you the triangular property of the basis, and therefore, that means that you see there is at least one column in which there is only one basic cell. So, if you now delete this, then in the remaining subset of basic cells, you now have this cell which is the only cell in the row, right. And then if you now delete this, then you can again find that, for example, this one is the only cell in its column, you delete this, then this is the only cell which is present in this row, I delete this, then this will be the only cell present in this column, and so on, right. So, once you do this, you delete this, then you will have this one as the only one, then I will delete this row and so on. This will be the only row, I mean this will be the only cell present in this one. So, you delete this, then it will come. So, you can anyway you try out, there will be always be a subset of the basic set of cells, such that only one of them is present in either a row or a column. So, this is the triangular property. The second property, as I am saying, that since this has to be present in every row and every column. So, now again in a very ad hoc way I am trying to say is that we can express any non-basic cell in terms of the basic cells as follows. Now, of course, this property is anyway already there, because since the basic cells form a basis, therefore, correspond to the m plus n minus 1 linearly independent columns. Therefore, any non-basic cell will also be expressible always in terms of the basic columns, and so any non-basic cell will be expressible in terms of the basic cells. And remember how we were doing it. We said that if you want the column E I E j to be expressible in terms of the basic columns, then you see you first look for a column which is in the same row. So, I go E I E k, right, which I am saying. So, these actually these are the circles. So, these indicate the basic cells, this is my non-basic cell. So, I will go across, and remember, because there is a basic cell present in the ith row. So, I can go from here to here, this is the idea, and suppose this cell is present in some column k. So, I will have something like E I E k, this is my basic cell, right. Then since there has to be at least one, because remember I have to express this in terms of the basic cells. So, I should have, because there is a plus 1 here which is not here, then I must have a column which has a minus 1 here. So, that to cancel this out this one, that means I am able to traverse along the column, the kth column. So, I will come down and maybe there is something like p k, there is a basic cell here in the pth row. So, I will have a column E p E k, right. Then again, because I want to counter this minus 1 by plus 1. So, I must have a column like E p E l, and so therefore, there must be a basic cell present in there must be a basic cell of the kind p comma l. So, therefore, I will travel along the row, and then similarly again you will travel along the lth column, because you want to counter this plus 1 by a minus 1. So, I come here, and then I will again travel along the qth row, and this I will come to. So, of course, I have just demonstrated one arbitrary way of connecting I j with the basic cells. So, essentially what we are saying is that this will form a, you will be able to form a cycle, and this is the only arc which is the non-basic cell, and the remaining basic cells they form a connected path like this, and then you have this. So, therefore, now you immediately know that I j can be the column A I j can be written as a linear combination of these basic columns. So, I am just trying to make you conversant with the array, and so you can translate all the concepts that we learned for expressing a non-basic column in terms of the, because remember our aim is to finally be able to obtain the column Yij, because to progress with the simplex algorithm I need the components Yij, and which are, as we know, are +1, -1 or zeros, but so I need to know which are the +1s or able to be able to continue with the simplex algorithm, and therefore, this is all is being done, so that I can just by having the transportation array right here I can compute my the necessary components of Yij and continue with the simplex algorithm. This is the whole idea, and I am just, so the connectivity. So, when we say that the basic cells span the transportation array, the whole idea is that the basic cells are in such a way that I can always take a non-basic cell and then connect it to the basic cell, so that I form a cycle, and then immediately I get how to express my column corresponding to the cell I j in terms of the basic cells. For example, this will be +1, this will be -1, +1, -1, +1, and all other Yij components will be zeros. Okay. And here again, this concept we will later on also spend some more time on it when I do network flows and so on. So, I am trying to say is that, see, corresponding to this transportation array 4 by 5, this is my bipartite graph, right, and you can see that these basic cells, they correspond to these basic arcs, which are my, right. So, this is the thing, right, and if you want to have a particular, see here, if you have the arc 2 1, which is a non-basic arc, then you immediately you see you can find out the cycle that you will form here. So, with this one, see, you will go this way, this and this. So, here also, so essentially the word that I have, I am not using it right now, but see, this is a graph, and here the m plus, and with m plus n. So, here for example, it is 9 nodes. So, I am saying that you take 8 arcs and they correspond to your basis, and they will form a spanning tree. This is and the spanning tree means, and that is why I use the word span there. So, spanning tree. So, now you take any non-basic arc, and then it will form a cycle with the subset of the basic arcs, and then you will immediately know how to express this column or this arc in terms of the basic arcs. So, this is the whole idea. So, all these concepts are the same. I am just trying to make you familiar, so that once we work out the simplex algorithm on the transportation array, you can immediately see what all is happening. So, therefore, now the next step would be to find out how we write down the components of Yij, and for this I will need the concept of a minimal dependent set, and also we will formalize this computation of the components of Yij. So, the concept of a theta loop, I want to introduce the concept of a theta loop, and this is a minimal dependent set. Of cells in the array. Okay. So, concept of a dependent set. Now, I have already told you what we mean by an independent set of cells. Now, we talk of a dependent set. Okay. So, theta loop is a non-empty subset of cells with the following properties. Okay. The first property says that every row and column of the array has either 0 cell, so 0 cell or 2 cells from this theta loop, right. Okay. So, I am trying to say that it is a subset of cells, and when does it qualify to be a theta loop? is that every row and column of the array has either a 0 cell from this set or 2 cells, right. And no proper subset of it satisfies property 1. So, you see, the moment I say that if no proper subset of it satisfies property 1, that means no proper subset of this theta loop of this set of cells will have two cells from it in the in a row or a column. And remember, by now you should have this clear in your mind, that if you have a collection of columns such that each of them has 2 entries, 2 non-zero entries, which is 1 1, then we know that that set of columns is linearly dependent, and the same concept is being translated to the cells of the array, right. And so, either so the array has either 0 or 2 cells. So, no proper subset of it satisfies property 1. So, therefore, you can see that it is a minimal dependent set. So, this tells you this, and let me now give you this theorem. Yeah, the theorem says that let beta denote a set of basic cells, which means that there are m plus n minus 1 cells here, which correspond to m plus n minus 1 linearly independent columns, right. And let cell R s not belong to B. Okay. So, it is a non-basic cell. R s is a non-basic cell, all the elements of B or script B are basic cells. Okay. Then union R s has a theta loop, and the cell R s belongs to the theta loop. Okay. So, the theorem is straightforward, and you can I can write down the proof or so. Okay. So, what are we saying here? That you start with a set of basic cells which are m plus n minus 1 in number, and then you add a non-basic cell to it. So, therefore, the number becomes m plus n, right. And then we are saying that this must contain a theta loop, and the cell R comma s must belong to this theta loop. Okay. So, now since B union R comma s has m plus n cells, that means the corresponding columns are m plus n in number, and we know that they cannot be linearly independent, because the rank of the matrix has been shown to be m plus n minus 1, right. So, therefore, the set union R s is a dependent set. Right. And script B was not a dependent set, right. So, so therefore, your script B union R comma s has a theta loop. Okay. Maybe I will agree that I am not giving you a very rigorous exposition here, but the idea is that you should just understand how we are translating the concepts of the simplex tableau or the calculations to the transportation array. So, but has a theta loop, right, and because one should talk of a uniqueness of a theta loop, which also I will mention and try to give you some rationale for it. But so, this has a theta loop, and since script B is an independent set, is a basic set, this theta loop is not in script B. Therefore, the cell R S belongs to the theta loop. You might say that little simplification of the arguments and so on, but anyway this tells you that because this is a dependent set. So, it must have a theta loop, and since script B is a basic set, it cannot have a theta loop. So, the theta loop has come because you have added the cell R comma S, and so the theta loop must contain the cell R comma S. Okay. Now, this and as I told you, I want to all this is leading to trying to obtain the vector capital Y I j through which has the components to how express the column A I j in terms of your basic columns. Okay. So, this is what we want to do. First of all, how to find the theta loop in okay. So, this is the next part, and here again I will give you a method. So, what it says is that how to find the theta loop in this. So, okay. So, start with all the cells of uncrossed. Okay. So, you begin with all the cells of script beta, script B union R comma S uncrossed. Now, cross the cell which is the only one in a row or a column. Okay. So, out of this you will certainly find one cell at least which is the only one in a row or a column, right. Then cross it and remove it from union R comma S, right. And then you repeat the same thing with the reduced set. Repeat this process with the reduced set. Set till you all the okay, till you do this till all the what I want to say is that you will repeat this, continue with this process till you are able to find one cell which is only which is the only cell in a row or a column, right. And when you cannot find a cell from this which is the only one in a row or a column, you will stop, which means that the remaining cells that you are left with have the property that every row in a column has two of them, right. So, this is what I want to say. So, repeat this process with the reduced set till all the cells, all the remaining cells are okay. Maybe I need to just this till all the remaining cells are maybe I should just okay, remaining till all the remaining cells form okay, I wanted to rephrase the sentence, right. So, that means all the remaining cells now will form a theta loop. That means they will have this property that every row or a column has either two of them or has 0 of them. So, therefore, this is the idea. But okay, now this is the thing is that you may, for when you are doing small problems by hand, you may actually just use an ad hoc method to locate theta loop. but otherwise this is the way to do it. And for very large problems, when you have hundreds of rows and hundreds of columns, then a regular labeling algorithm is used for locating a theta loop, because that itself will require a lot of effort and you want to streamline it so that you do not spend too much time. So, for large matrices, okay. So, one can just use, and that is what will happen when I am solving a problem. I will just use the ad hoc method and maybe not always use this method. And the labeling algorithm of course has to be programmed, and then it has to be part of a software for solving transportation problems. So, for large matrices, labeling algorithm, labeling process described in section 11.4 of K.G. Murthy's book. I have already given references, K.G. Murthy's book is available. Okay. Simple labeling procedure, but it sort of streamlines the search for a theta loop when you have a large array and you want to locate a theta loop. Okay. So, therefore, this can be done, right. Now, let me get to this, how do we try to get these numbers, the vector y I j. And so, let me so let me just first give you an example here quickly. Say for example, if you have a 6 by 4 array, and I will just show you the basic cells here. This is a basic cell, this is a basic cell, okay. And then you have a basic cell here. Oh, we don't need the numbers, just the collection of cells, and then okay. Okay. So, 6, 4, 10. So, you should have 9 basic cells, 2, 4, 5, 6, 7, 8, 9. So, these are the collection of your basic cells, and suppose I have this non-basic cell here, then it becomes this set of basic cells, which is 10 in number, must contain a theta loop. And so, therefore, see, I will to locate the theta loop, we said that we look for a cell which is the only one in a row or a column. So, I will cross this. Once this is gone, now you look for another cell which is the only one in a row or a column, and this is the one. And now, after this, you see every row and column in which the cells are there. So, these are 2, right. And so, you have a theta loop, and you should be able to connect the things. So, here you see you can do this way, this. Okay. So, this is the thing. So, you have a theta loop. Okay. Now, I want to quickly show you how to locate. Okay. So, now the theta loops used for obtaining y I j, as I told you earlier. So, the thing is that now I will probably just give you an example here instead of, and then you can always formalize it. See, for example, now this is the basic non-basic cell, and you would want to express it in terms of the non-basic cells. So, this is, for example, this is 3 3. So, you are having A 3 3, and how can you write it now? You see, again, as I have explained this procedure to you earlier, you are going up here. So, therefore, this will be A 1 3. Okay. Then you are coming down this way. So, alternately plus and minus. So, you are coming down to minus A 1 1. Then when you come down here, this will be plus A 4 1. Okay, and I will let you do the arithmetic. A 4 1, then 1 2 3 4 5. So, minus A 4 5, right, and then you are going up. So, this will be plus this is what 1 2 3 4 5. So, A 2 5 and minus A 2 4 plus 1 2 3 4 A 3 4. Okay, please check out the arithmetic, that this will be, this is the representation, and you see through the theta loop you can get the, that means your the component of, when you write the vector y 3 3, you see this will be because you have n basic cells. So, therefore, it will be an n dimensional vector, and so here you start, say if you have the convention that this is the first component, second, third and so on. So, accordingly you will have something like 0 0 1, then you will have a 1 1. So, a 1 1 is minus 1 and so on. So, in any case this is the expression that you can immediately, just by looking at the array having the theta loop in which your cell is present, the non basic cell, then you can have this expression and you can find out the components, and this we will later on also use when we are doing the parametric analysis. And see, actually what I should do is, if I want to look for a particular component here, say for example, this one, then I should have refer to this as 4 1 or something like this. But later on when I am doing the parametric analysis, I really do not distinguish between, the idea is that you are taking a particular component from this vector y 3 3, and as you see, and as we have also already mentioned, because of the triangular property, that the components of y 3 3 will be either 0, plus 1 or minus 1, which is evident from here. Okay. So, the components of this will be this, and now you see that once you have these numbers, then you can immediately obtain, which I have explained, we will explain to you later on also, that is, if suppose this is a cell which is to become basic cell, then you will have plus theta here, you minus theta, plus theta, minus theta, plus theta, minus theta, plus theta and minus theta, right. And so, from here putting the constraint of optimality, of feasibility, because you want this to come at a level theta, which means that you must make sure that the none of the basic variables becomes negative, and so from there you will be able to get a value for theta, and so you can obtain a new basic feasible solution. So, now I am telling you that if you have a set of basic cells, one can run this labeling algorithm to find out if there is a theta loop or not, or in the process when we are locating, when we are giving out the values to these basic cells, we will discover whether there is a theta loop or not, right, and you will see how. So, for example, here there is a basic set of cells, and remember there will be at least one row or a column which has only one basic cell, because all rows and all columns cannot have two, otherwise it will become a dependent cell. So, I see here that in this column, this is the only entry. So, we will give the value 8, right, to satisfy. So, once this is satisfied, this is out, this column is this constraint is satisfied. Now, because I have made an allocation here, so I move along the row and I will find a entry, or you can keep applying the same rule, that is, I first look for a row or a column which has only one basic cell in it. So, I make the allocation according to whichever value is the minimum of the two, the row and the column number. So, this becomes this. Then you see this becomes 3, because I have already made 8 units of allocation in the first row. So, that means the first market is from the first supply point, I have already used 8 units, right. So, then I look for this row, and or I look for a row which has only a single entry, and this now has single entry, row or a column, whichever. So, this has this, and since for this one 3 is the leftover now and 13 is this, so minimum is 3. So, I cannot make allocation of more than 3, right. So, then this row is complete, that means this supply point is completely used up, right. Okay. Then if you come down, you see again you look for a row or a column which has a single cell, this is the one. So, here I can make a allocation of 10, right, because this is 13. So, this will be gone and this will get updated to 5. Then you see that here this row has only single entry. So, 5 and 13 I will make 5, then accordingly you go 8 here, right, and this is 6, Oh, okay. No, this is not helping me because, okay, so what is going wrong? Why did I see if I make this here, yeah, then this has to be 8, and yes, so that means of course if you look at, so do I have a, no, so this is a set of basic cells. So what is happening is that if I make 6, yeah, okay, fine, no, yeah, right, I am sorry. So this is not, yeah, right, I will tell you what is the problem. See here, this is 11, and this, if I make this thing 8 here, then this will be 6. So there will be a problem if I make 6 here, then this remains. So that means I can only do, so this will not be satisfied. So therefore, what I need to do is I have to make 11 here, because this is the only entry in this column. So I have to make 11 here, and since this is becoming now how much, 19, I will have to make an entry of -5 here. So that I do not use, and we have to understand what we mean by this, right. Okay, so -5, if I do it, then you see this is 12, this is the only entry, and then this is 7, because my supply requirements is the same as the number of amount of supplies, right. If you add up these numbers, they all add up to 23 and 14 is how much? 23 and 14, 37 and 15, 52. So both these numbers add up to 52. So the supply is equal. So it's a balanced transportation problem, no problem. But see, so this is what I wanted to show you through this example, that this is a set of basic cells. It satisfies the conditions for being a basic set of basic cells, but it will not lead you to a basic feasible solution. Okay, which means, so as you saw, for example, when you were looking at the system Ax equal to b, x greater than or equal to 0, we had a basis which need not lead us to a basic feasible solution. It will give us a solution to this system, because I have a basis here, so it will give me a unique solution here, but the components of this solution may not be all non-negative. So it will not be a feasible solution, right. And this is what I was showing you, that every set of basic cells need not lead you to a basic feasible solution. So this is not a basic feasible solution. And now I want to show you, give you a rule for obtaining a basic feasible solution very easily, and that is known as the northwest corner rule. And later on we will look at many more methods for obtaining a starting basic feasible solution, right. So here the idea is very simple. Northwest corner rule to, maybe I should complete the thing, to obtain a basic feasible solution. This is the idea. So the next question is, how do we go about obtaining a starting basic feasible solution? And we do not need phase 1 or anything here, because of the structure. We are exploiting the structure, and you see how simple it is to obtain a basic feasible solution. And we already said that once it is a balanced transportation problem, it will always have a basic feasible solution. So let us see, what you do is you start from the northwest corner rule, and that is why the name. So start from here, look at the two numbers, and you can allocate 7 here, right. Once you have done this, this column is cancelled out, whichever either the row or the column number will be satisfied. So you cancel out the corresponding thing. Then you have, because this is still left over, there is a element 4 units still have to be used from this source. We will move along the row, and I will make an allocation of 4, because this 4 and 8, this is the minimum. So always check, right. Now this is 4 here. So I have to move along the column. Okay, we move along the column, then 4 and 12. So I cannot make an allocation of more than 4. So this way, and then this is 8, and so move along the row. When you come here 8 and 11, this is 8, right, and this becomes 3, this is satisfied. Now sorry, so I move along this is not, yeah, only this row gets cancelled out. Then I move down the column, because this is still to be satisfied. So therefore this will be 3, because 3 and 14, the minimum is 3. So this is this. So this gets now cancelled out, and I move along the row. This is 11, 11 and 13. So, this is 11, right. So, this gets satisfied, then this is 2, you come down the column, this will be 2, and now you see this is 13 and 13, 13, because the last constraint will always be satisfied automatically, and that is why we drop it from the constraint system, and now you have a feasible solution. Why is it a basic feasible solution? Because I am satisfying a row or a column constraint at a time. So, therefore, first of all, this is, yeah, let me, so the solution obtained is a basic feasible solution. Why? Because it will have exactly m plus n minus 1 cells. So, you can do it for the general case, right. I have shown it to you for a 4 by 5, but this will happen, it will have exactly a, because why? Because a row or a column constraint is satisfied at each basic cell allocation, at each basic cell allocation. Okay. So, therefore, because the last one will get satisfied automatically, therefore, exactly m plus n minus 1 cells will be allocated, and why will it not have any theta loops? Because I will never go back. You see the movement, the way the movement is, and no theta loops present. Yeah, you can argue it out yourself, no present. So, this is a basic feasible solution. Just see how easy life is. In case a row and a column constraint are satisfied simultaneously, this is while discussing the northwest corner rule to obtain a starting basic feasible solution. So, if a row and a column constraint are satisfied simultaneously, then we will move diagonally, because I can't move horizontally or vertically, since both the constraints are satisfied. So, this will result in number of basic cells less than m plus n minus 1. But then we can add the required number of basic cells at 0 level, so that theta loops are not formed. So, this can be done, but in the northwest corner rule, actually what we do is we still move either horizontally or vertically and add a basic cell at 0 level, because both the row and the column constraints are satisfied. So, we will just move across horizontally or vertically and put a 0 in a basic cell, so that the number of basic cells remains at m plus n minus 1. We will discuss this further when we are talking of degeneracy. So, this gives you a basic feasible solution, and then we said that I want to show you that, for example, if you just add this cell, that means you want to look at the current. So, that means now look at the union 1 4. Look at this, 1 4 is a new cell. So, this is going to be a dependent cell. So, how do I discover, how do I locate the theta loop? So, what I will do is, as I told you, the procedure is you start from here. Then you either look at along the row or the column. So, I look along the row, this is the basic cell I hit, right. So, we will put plus theta here, this will be minus theta. Then once I come here, I move down the column, right. So, second column, and I come here, this is my basic cell, right. So, this will be plus theta, let me write plus theta. Then I move along the row, I come here, right, and this will be minus theta. Then I move down the column, this will be, this is minus theta, this is plus theta, then you move here, right, and this will be minus theta. And you see I am in the same column, so I get connected. So, this is the path or the theta loop. Okay. And plus theta, minus theta, and you can see that this set, this is a subset which is present here, and 1 4 is part of the theta loop, and these two columns, these two rows have two theta cells, theta loop cells, and this column has it, this row again, this column, this row, and then this column. So this is how you can locate a theta loop in this, and you see that once you locate the theta loop, how do you obtain a new basic feasible solution from the given basic feasible solution. Yes. So, you can immediately see that if I want to bring this at a level theta, then this will go down by theta, this will go up, this will go down, go up, go down. So, therefore, the ones which are going down, I have to make sure that they remain non-negative. So, here theta cannot be less than cannot be more than 4, and similarly here 8 and 11. So, I will choose the minimum of them. That means, if I take theta, choose theta equal to 4. This will make what? This will make this cell 0. So, that becomes non-basic. This will become a basic cell. And so, you have a new set of basic cells which do not have a theta loop in them, and they give you a new basic feasible solution. And so, one has to just now see, so that means you have so many options. So, which basic cell, which non-basic cell to choose to enter the basis. We will look at the relative prices, and I'll show you that how easy it is to compute the relative prices, and then continue with the simplex algorithm for the transportation. So, we just continue, and let me show you how how to again locate a theta loop, and to obtain, that means you are given a basic solution, sorry, not even you are given a feasible solution, and how to obtain a basic solution, basic feasible solution from it. So, obviously, a feasible solution, if it is not a basic feasible solution, it means it has a theta loop. So, we will locate a theta loop, remove it, and get a basic feasible solution, right. So, here look at this example. So, these are the supplies. Okay. Normally, I should write here, this is SI and this is your DJs. These numbers give you the cost, the CIJs for the cells, and the circled numbers give you the values of the variables. Okay. So, here is a feasible solution, because 4, 5, 9, 3, 6, 9, then 11, 21, 3, 24, 1 plus 2 is 3, right. Similarly, all the demand constraints are satisfied, 3, 12, 12, 8, and then 10, right. So, this is a feasible solution, but it is not a basic feasible solution, because how many variables, positive variables, 2, 4, 7 and 2, 9, whereas we should have a basic feasible solution should have 8 basic cells, right. So, therefore, a theta loop is present, and again we just start from somewhere. Let us say I start marking this. So, this becomes plus theta, right, and then I will go to yeah, okay. The thing is that if I go here, I should, because the connectivity is there. So, I should be able to locate a theta loop, and therefore, because I see that here, yes, and that is why the labeling method is needed when you have large set. So, I will go here. So, this will be minus theta, right, minus theta, then I will come here, remember. So, this will be plus theta, right, and then I can go, because if I go here, then there is nothing else to move up and down. So, therefore, I need to move here, right. This will be minus theta. Now, here again I have to come down, because there is nothing, no basic cell upstairs. So, this is the one, right. So, this becomes plus theta. Then I can shift here, right, this way, and then this. So, you see you have this. So, the path that you have, the theta loop that you have is, consisting of the cells 1, 3, 1, 4, right, 1, 4, and then here this one is 1, 2, 3, 4. So, 3, 4, and then 2, 4, sorry, 4, 2. No, this is 3, 2. I am sorry, yeah, see from here. So, this one is 3 4 and then yeah comes to, so 3 2 3 2, then you come down 4 2 4 2 4 3 4 3 and then you see you are back because you started with 1 3. So, you are back to 4 3 and then this one, right. So, this will form a theta loop when you combine here. Okay. So, this is a theta loop and plus minus. So, now we want to get a basic feasible solution from this one. So, this is plus theta, this is minus theta, right. So, look at the minus thetas because, so here for example, from here theta can be 5 at most, then you come down here, this is plus, this is minus, theta can be 11, right. Then this is plus, this is minus, so theta can be 2. So, therefore, the smallest value permissible of theta is 2, and so I will put theta equal to 2 and this will be gone, this basic solution is gone. So, remember here plus you have to make it 3 because the row and the column constraints have to be satisfied. This is minus, so this becomes 9, right, this becomes 5 plus, right, then this is minus, so this becomes 3 and that is it. I think we have taken care of. So, we will just make sure that the row and the column constraints are satisfied, right. This one becomes 6. Yeah, so a check is needed because you should make sure that you have. So, 6 plus 3 is 9, 6 is 12. This of course was not disturbed. Then here this is 14, 10, 24. This is 12 and this is 8 and that is it. So, this is now a basic feasible solution that you have obtained. So, let us now proceed with the method for computing the relative prices. So, we look at the dual problem. I will rewrite your transportation problem. Primal is minimize z equal to summation Cij Xij, right, where I belongs to your V1 and j belongs to V2, right, subject to summation Xij, j varying from 1 to n is equal to Si, I varying from 1 to m, right. These are your supply constraints and summation Xij summation over I varying from 1 to m is dj, j varying from 1 to n. And right now we are looking at simply this for all ij. Okay. This is your primal problem, and as we said, every column has only 2 entries plus 1, or well, in this case we are writing plus 1 plus 1. So, what will be the dual? This will be maximize. So, we will associate with this ui and with this vj just to distinguish. So, ui's refer to the supply constraints and vj's refer to the demand constraints. So, maximize psi equal to summation C S I u I varying from 1 to m plus summation dj vj j varying from 1 to n, right. And since your primal constraints are all equality constraints, there will be no restriction on the sign of the dual variables, but it is a minimization problem. So, subject to, yeah. So, now you see each column here becomes a row, right. So, a column has only 2 entries. So, there will be one entry corresponding to ui and the other corresponding to vj, because look at the column aij has an entry ei and ej. So, subject to ui plus vj less than or equal to cij. So, a simple structure, no restriction on the signs of. So, you can say that ui greater less than 0, vj for all I and j, right. So, therefore, you see the calculation, remember the dual feasibility implies primal optimality, right. So, and here the relative prices are simply, yeah. So, I will not spend time here because you should be able to figure it out yourself. That, so, therefore, the relative price, that means your Cij bar is nothing but Cij minus ui minus v. minus Vj. So, the relative price for ij is this, and so you can simply check. So, but anyway, so first we need to find out the ui's and vj's. So, if I can calculate the ui's and vj's fast, then no problem. I can then just find out the difference of the right hand side from the left hand side, and that gives me the relative price for each non-basic variable. So, now let us see how many equations, because since m plus n minus 1 basic cells, this implies ui plus vj is equal to Cij for ij belonging to the basic set. So, I will refer to the script B as the basic, the set of basic cells, right. So, this is your, so but I have m plus n, but there are m plus n dual variables, right. Now, since the the m plus nth constraint is dropped, we can choose Vn to be 0. So, once I choose Vn to be 0, because the last constraint is dropped. So, therefore, if Vn is 0, then the product will always be 0, right. And in any case, it is a balanced thing. If you are working with a feasible solution all the time, then the last constraint is anyway satisfied. So, actually it is not really important that you choose Vn as 0, you can choose Vn to be any number, right, because the last constraint will automatically be satisfied. So, then once this, therefore, then you will be left with m plus n minus 1 dual variables to compute, and you can do that uniquely from these m plus n minus 1 equations. But again, because your this thing is triangular, because your basis is triangular, therefore, can compute the remaining m plus n minus 1 dual variables by backward substitution. Okay. So, since Vn is 0, you can choose, you can immediately compute the ui's corresponding to Vn, and then because there will be cells present in the last row, and then you can go on by backward substitution, you can compute the other this thing. So, then once you have the ui's and vj's, you can find out the relative prices, and you can proceed with the, so the optimality criteria would be, yes, optimality criteria is that Cij minus ui minus vj are greater than or equal to 0 for all ij, right. So, if you find a cell which is for which this is less than 0, you will proceed with the simplex algorithm, and that means that cell will be ready to enter. And we saw that if you to the basic set you add a non-basic cell, it has a theta loop. So, in the theta loop you do plus theta minus theta, you get a new basic feasible solution, again update your dual solution, and so you can proceed with the simplex algorithm. Yes, I mean I do not have to spell out the things because it is all very clear. So, let us quickly look at this thing here. So, for example, by the northwest corner rule, the same problem. So, we have these, this is the basic feasible solution, starting basic feasible solution, and as I told you, if I put the corresponding, so this will be columns for columns. So, Vn I am putting it to 0, and immediately you see that since the sum of these two numbers should be equal to this. So, my u4 will be 5, right. Is it okay? Once this is 5, then remember the number here, this plus this must add up to minus 3. So, that means this should be minus 8. Is it okay? because you see for the basic cells the dual constraints have to be satisfied as equality, right. So, here the corresponding dual equality constraint is see this is 1 2 3 4. So, U4 sorry, this is V4 plus V4 plus U4, yeah, this is 4 4 should be equal to minus 3. So, now I know that U4 is 5. If U4 is 5, V4 will become minus 8. Now, this is minus 8. So, this is backward substitution, minus 8, and remember here this is 2. So, the number here will be 10, because 10 minus 8 will be 2. The equation has to be satisfied, right. The inequality has to be satisfied. Then once you have this as 10, this is 2. So, I need here this will be minus 8 again, right, because minus 8 plus 10 is 2, right. Once this is minus 8, I go up, and here this is 14, because 14 minus 8 is 6, and 6 is equal to 6, right. Once you determine this, then you come here, and this will give you how much? 12, sorry, minus 12, yes, because 14 plus minus 12 will be 2. So, this is minus 12, this is 4, so this must be 16, and if that is 16, this is 10, so this must be minus 6, and you can immediately, so backward substitution method gives you an easy way to compute the dual solution. Once you have the dual solution, I can now compute the relative prices for the non-basic cells, which is again simple, because it has to be 12 minus, so add up these two numbers, this is 8. So, 12 minus 8 is 4. Yes, please sit down with a paper and a pencil, and you can do the work out the thing. So, now here this is 1 minus, this is 8, 1 minus 8 is minus 7. So, this is negative, right. Then this is 8 minus 16 minus 8. Yes, 8 minus 16, this is 0. Similarly, come here, and this will be minus 3, and then that is 8. So, minus 8 minus 11, right. Then this will be 3 minus 6, 3 minus 6 will be minus 3. Then this one is minus 1, so 14 minus 15, yes, and here if this will be 2 minus 4, 2 minus 4 will be minus 2, yes, please check my calculation also, 4 minus 2 minus minus 2, so this is 6, right. Then this will be 1 minus 10 minus 9, and here this one will be 10 minus 1, so 11, and this is minus 7, right, minus 7, so minus 2 plus 7, so this become 5, yes, yeah, this is minus 2, and then you have minus ui, which is 5 plus 12, yes, 7 5, okay, that's right. So, then this will be 5 minus of 3, so which will become 8. So, this is it. So, this is your relative prices. We will go for the most negative one, and later on we will have a discussion why. So, therefore, let us say I go for this one. So, that means you have to scan and find out which is the most negative one, but remember the Bland's rule said that you can choose the first negative one. So, I do not have to compute it. And for large problems, we will have to do something like this, because for example, when I hit this one, I should have just stopped here and decided to bring this into the basis, right. So, anyway, so now you see that you have to form a theta loop, that means this is going to enter the basis. So, this will be this, yeah, up and down. So, horizontal, vertical, horizontal, vertical, and this is it. So, here theta, if you put this plus theta, will be minus theta, plus, minus, plus, minus. So, that means theta can be equal to 8, right, because this is minus, plus, minus, plus, minus. So, the minus ones require you to be, it is 8, 11 and 13. So, the best value that you can choose for theta possible is theta equal to 8. That means, now you will have a new basic feasible solution, and actually you can also see once you get a little feeling for the algorithm, is that you see these cells do not get disturbed, right. So, I just need to update part of the dual solution. I do not have to even update the whole dual solution, and then you can see that you will also not need to update all the relative prices. You can just that will come by experience, but anyway, for large problems you need there are good programs written for the transportation problem. But you see the simplification that comes through the because of the special structure. The transportation problem has a very special structure, so you do not need so many different computations, and you can just see how the things are progressing. So, therefore, you get the next basic feasible solution, and then you have to check for optimality. So, here also I would like you to see that for this problem, for example, if you compute the dual variables, then this probably will turn out to be an optimal solution. That means, now this check for optimality for this, right. So, what I want you to do is to, after you have updated this, check for optimality. Check for optimality. So, I want you to work it out yourself, obtain the dual solution, and then you see that all relative prices will be non-negative. So, I think we will stop here and then continue with the other parts of the other aspects of the transportation problem.